Today I will be presenting a work that I have been doing with my collaborators, and I want to acknowledge them as Saki Lee, Dongmin Kim, Andrew Wittenberg, and Sanwook Ye. And they have been very, very helpful with this regard and very, very difficult task. So today I will be presenting about future changes in El Nino spatial temporal distribution under anthropogenic climate change. An outline of my talk here, I'm going to present some motivation why we care about El Nino, especially under climate change. I will describe the methodology we use, and then we will see some results with regard to El Nino under greenhouse gas, GHG. And we're going to see how does El Nino growth and decay under external forcing and what expected changes we might see. We will see also what kind of role does the mean state changes plays into ENSO evolution. Also, we will look into weather noise influence. I'll call here a stochastic forcing influence of El Nino in a future climate and some potential remote impacts. And then I'll present some concluding remarks and future work. First, for the motivation, why we care about El Nino. El Nino is basically the dominant mode of global climate variability in our planet. It presents itself, the warm phase is basically a relaxation of the mean state in the tropical Pacific. Under normal circumstances, you see that convection is often found over the warm pool of the tropical Pacific Ocean. And then we have a cold tongue over the Eastern Pacific and a slope thermocline. And this drives what is known as the Walker circulation, where you have the trade winds going from east to west, increasing moisture transport towards the west, and also supplementing convection here. Under El Nino conditions, we have a relaxed mean state where this atmospheric convection tends to shift westward following the warm SST anomalies. So as you can see that during El Nino condition, the thermocline relaxes, the thermocline slope relaxes, especially on the Eastern Pacific, where it deepens the thermocline. You have a warm SST anomalies over the Eastern Pacific and a shifting convection eastward. And this is all explained by what is known as the Sweepback, where all these three processes are linked together. Oftentimes, we study El Nino based on indices. We have atmospheric indices, but the most common are the oceanic indices here described in the bottom picture here, where we have different Nino indices like Nino 1.2, Nino 3, Nino 3.4, and Nino 4 to describe what's going on in the Pacific Ocean. Why we care about El Nino? Well, like I mentioned before, this event is basically our best and our go-to event when it comes to extended weather forecasts. And I'm talking about from the seasonal to the interannual timescales. It actually have a great influence in the atmosphere, as you can see here by the diagram, where you have an El Nino. You tend to have a southward shift in the Pacific jet stream and an intensification of the storm track, basically, which actually transport moisture towards the continental US, especially in the southern part of the continental US, and also influence drought occurrence over the northern portion of the continent. During La Nina, the opposite occurs. We have more of a meandering of the jet stream due to weaker atmospheric eddy activities, and you have kind of like an opposite pattern. So this helps us kind of like issue seasonal forecasts, for example, for extreme events such as extreme temperature events and extreme rainfall events, including droughts. And the largest impact is often found in the boreal winter and spring, when El Nino signal is the strongest. Beyond the changes in atmospheric circulation due to El Nino, also the spatiotemporal distribution of El Nino is very important, and as well as how that might change in the future. there has been many studies using couple model intercomparison projects where the models are forced by an external forcing, which is an anthropogenic forcing of greenhouse gases. And what is found is that the El Nino event may intensify and also the occurrence of the event may increase. However, these previous studies rarely look at the diversity of El Nino in terms of their evolution, temporal evolution. And recent work have been looking at the spatial distribution of El Nino in a changing climate, but the spatial temporal distribution hasn't been studied well. And this is very important because in this plot here on the right, this is a study from one of the co-authors here in our paper, Sankey Lee, shows that this spatiotemporal evolution of El Nino is key to predict U.S. rainfall, especially in the southwestern U.S. And as you can see here, the three big El Ninos, the most recent ones, the 1982, 97, and 2015 El Ninos, they were kind of like the biggest El Nino in our recent record. And this last El Nino, there were lots of hope for a rainfall in the western U.S. because we have an outstanding drought during this period, and forecasters were believed that due to El Nino, this drought will be reduced because of potential impacts in rainfall, as you can see here from the 1982 and 1997. However, this study from Lee et al. Found that it's not so much as the amplitude of El Nino, but also how much does it persist into the spring, and whether El Nino persists into the spring specifically over the Eastern Pacific. And as you can see here for the 2015 event, there was very little SST signal in the springtime near the Eastern Pacific. So this called for the need to better understand not only the spatial changes, but also the temporal changes of El Nino in order to improve climate predictions, but also we want to understand how El Nino may change into the future in order to understand climate projections. And this is what we're trying to get here. To do so, of course, since we're dealing with climate change, we're going to rely on a couple model integration. This is, we're going to rely on the large ensemble simulation from the NCAR Community Earth System model. And this simulation follows the CIMIP-5 protocol, where we have a pre-industrial simulation, thousands of years of pre-industrial simulation. Then we have several ensemble members, in this case, analyzing 30 ensemble members from the large ensemble that mimic 20th and 21st century projections. So for the 20th century, we use the observed composition of the atmosphere. For the 21st century, we use a projection, which is the most pessimistic projection, what is known as business as usual, or the RCP 8.5. This model is, like I said, it's an Earth system model. It has an atmosphere, ocean, sea ice, land component, glaciers, and a coupler. And they work in unison to kind of mimic what we know about the state of the climate and how the climate communicate between each components communicate. For the atmosphere, it has a 30 vertical levels and a resolution of about 1 degree. And the ocean has a resolution of 1 degree as well, and 60 vertical levels. And this model has been shown to be one of the better models. I wouldn't say the best. It's one of the better models in the CIMIP-5 archive that reproduces El Nino variability and their teleconnection as well. And here on the left, you see this is a plot that shows El Nino 3.4 SST anomalies. This is the pre-industrial simulation for 1,000 years. And this model shows an El Nino power spectral of about 2 to 6 years. That's well within the observational range, and an autocorrelation of about a little less than a year, which is also as observed. And very important, it shows a very nice El Nino variance, seasonal variance, which is, this figure is basically trying to quantify when we might expect the time of emergence of the anthropogenic climate change signal on top of natural variability. Here, what I have on the gray area here is from our pre-industrial simulation. This is basically the uncertainty range due to natural variability. And you can see here about year 2030 in this model, specific model, and a specific external forcing, RCP 8.5, we might expect the anthropogenic climate change signal to emerge by about year 2030 when it comes to the number of El Niños. So now here, this plot, what it shows is the spatial temporal distribution of El Nino as the event evolved, starting in year 0 here, the time increases up. So this is June, July, August of the developing phase, all the way to June, July, August of the demise phase, year +1. And then on the left panel is the 20th century evolution. On the right panel is 21st century minus 20th century, so the expected difference. And you can see here that El Nino seems to develop faster and reaches a larger amplitude and persists longer in the 21st century. But if we study El Nino changes in the future based on, let's say, a fixed geographical index like Nino 3.4, you can see here that there are places where you have warm anomalies, other places where you have significant cold anomalies, so you may not see these changes. Therefore, the importance of looking at El Nino in more of a diversity type. And this is what we're doing here. You will see lots of plots like this from now on. This is a Mueller diagram of the evolution of the event across the Pacific, average from 2 north to 2 south, and the evolution. This is a composite. El Nino, you see, peaks in January. And the left column is for the observation, then CSN 20th century for the 20th century, CSN 21st century, and then the difference between 21st century minus 20th century that we may expect. On the bottom row, the same thing as the top, but this is for the observed precipitation anomaly, and then for the models. And you can see that the model does pretty well in terms of the amplitude of the event. This is well known that this model tends to have a little higher amplitude and variance compared to observation. The biggest bias is, of course, in the precipitation when you kind of have double maximum in the precipitation, especially in the growth phase during the summer. This is also a well-common bias in these models. But overall, you see that for the 21st century, you see that there is a large distribution of positive anomalies and negative anomalies. So it's not very clear whether El Nino will intensify or not. It depends on the location. For example, during the growth phase, El Nino will be higher amplitude and also growth at a faster pace in the Central Pacific. However, during the demise phase, the SST anomaly seems kind of like shifting towards the Eastern Pacific, where you will have more cold anomalies over the Central and Western Pacific and persistent SST anomalies during the spring, boreal spring in the Eastern Pacific. And this is corroborated with the precipitation signal down here. So there is a shift in convection eastward and more persistence towards the late winter and early springs. So we want to understand what's driving these changes in the spatial temporal distribution. For this, we will perform a mixed layer heat budget for the tropical Pacific. Here, this is just the thermodynamic equation where we'll have a heat storage term, a tendency term on the left-hand side, and several heat advection and radiative forcing terms on the right-hand side. Here, rho Cp is the density and specific heat of seawater. This is assumed to be constant for the problem here. T is temperature, UMW are the zonal and vertical velocities. And we're going to evaluate this heat budget for the upper 75 meters. This is kind of like a deep mixed layer heat budget for the Eastern Pacific, but it's kind of shallow for the Western Pacific. And for the problem here, we're going to assume constant depth. just to simplify the problem. I'm following the Inesio 2009. And there's lots of assumption here. And also we will have a residual term. This residual term contains, as you may expect, the surface net heat flux. It also contains the meridional advection terms, the diffusion heating terms, as well as unresolved subgrid heat fluxes and sub-monthly scale heating. That is resolved by the model, but it's no use here because we're dealing with monthly data. And this is a very busy plot. I'm showing you here, again, a whole mirror diagram, just like you've seen before. Actually, SST anomalies, you've seen it before, is on the right-hand side. The top row is for the 20th century, and the bottom row is the difference between 21st century minus 20th century. Here, each term is represented by a column, the heat storage term on the left-hand side, and then each feedback terms. These three feedbacks, thermocline, zonal advective, and Ekman feedbacks, are the common feedbacks that are believed to be dominating also El Nino growth, and then the residual terms. I want to probably start speaking about the residual terms. As you can see, mostly they are damping terms, and here the green contours represent the heat content for this mixed layer. And basically, you see when you have a positive heat content, the residual terms to be negative. So overall, the residual works towards damping the SST, the temperature anomaly. So going back to the tendency, basically, what you see here as color in the tendency column, the first column, is the time derivative of the heat content. So you can see that there's positive tendency during the growth phase and negative tendency on the demise phase. And moving to the left, you see that the thermocline feedbacks is the one that explains the best this tendency or this temperature tendency of the mixed layer, especially over the Central and Eastern Pacific. The zonal advective feedback explains well, especially during the growth phase, over the warm pool edge. And the Ekman feedback explains better what's going on near the Eastern Pacific because of that's where the upwelling and the stratification are stronger. But more importantly, when you look at the difference here, the bottom row, you see that very clearly the stronger growth in the tendency in the early part of the year, and then also some growth over the Eastern Pacific during the peak of the event, making the event persist longer. And also you see that the thermocline feedback doesn't change, kind of like spatial distribution, mostly the spatial temporal distribution of the feedback doesn't change. It's mostly an amplitude change where the thermocline feedback gets enhanced during anthropogenic climate change. The zonal advective feedback is similar, although it's weaker change, but you still see potential for growth during the growth period, especially in the Central Pacific. Very interesting is the Ekman feedback. It has kind of like a triple maximum signal in their difference. Especially it contributes both in the growth and the persistence of the event, especially in the Eastern Pacific. So we're gonna discern more, we're gonna look into more detail what's driving these changes in the feedback, because as you can see from the equations, they depend as well on the changes in the mean state. This overbar here represents the mean state and the prime represents the anomaly. So for example, the Ekman feedback, the mean changes in the mean stratification may play a big role. So we want to look into that. There has been many studies looking into potential changes in the tropical Pacific couple system, and there has been several theories that trying to understand what might happen under anthropogenic forcing. One theory is the ocean thermostat, which basically suggests that under greenhouse forcing, the zonal SST gradient may be amplified. So you may amplify the cold zone, for example, become colder or less warmer than the warm pool. So it end up amplifying the mean state. Other competing theories, also ocean dynamical theories, the ocean tunnel, where asymmetric warming between high latitudes and the tropic may influence the tropical Pacific upwelling region through basically oceanic meridional heat transport. And actually, it's believed that the zonal SST gradient under anthropogenic forcing, under this mechanism, the ocean tunnel may decrease. So in effect, you reduce the upwelling in the Eastern Pacific, so the zonal SST gradient becomes more homogeneous. There's also atmospheric perspective from climate change. One is looking to the evaporated damping. For example, under greenhouse gases, the atmosphere doesn't care about the SST anomaly. What it cares is more of the complete SST. So if you have a kind of like a homogeneous warming, you may expect more evaporated cooling or damping over the warm pool because it's already warm there. So in effect, this will also reduce the zonal SST gradient. And also there is the theory of about slowdown of the Walker circulation and the Variance feedback that I explained earlier, which also will reduce the background state zonal mean. So we look into what's happening in this model. We see that on the top row, this is for the 20th century, SST, thermocline depth, and precipitation. Again, as a function of longitude and time. Here, these are repetitive patterns because these are climatology, but I wanted to include 2 years just to make it easier for you to relate back to the anomalies. And on the bottom row is what is the changes we might expect based on what this model is telling us, 21st century minus 20th century. You see that this model is suggesting a general warming of the Pacific Ocean, but the warming is mostly concentrated over the central and eastern part of the basin, over the cold zone. Also, the thermocline seems to be relaxed. Based on the thermocline depth changes, you see like a shallowing of the thermocline on the western part of the basin and deepening of the thermocline on the eastern part of the basin. And also we see enhancement of the precipitation signal. So in effect, this, especially in the central and eastern Pacific, so in effect, this is kind of like suggesting a strengthening of the Earth-sea coupling in the eastern Pacific. So all this seems to suggest what we see from the anomalies changes, that it supports a stronger developing of El Nino and the persistence of the event in the boreal spring. And we will see that later. And this is a vertical structure from the model. The top is in color. What I'm showing you is the difference, 21st century minus 20th century temperature changes over 300 meter depth. And the lines here, the black line is for the 21st century, the blue line is for the 20th century. And you see the thermocline relax, and as well you see enhanced stratification, especially on the central and eastern Pacific. On the bottom here, I computed the variance ratio. This is 21st century over 20th century interannual variability ratio. And you see here kind of like a tripod pattern where right above the thermocline depth, the mean thermocline that you see enhanced variance, and right below it you see reduced variance. This suggests that, again, could be linked to equatorially trapped Kelvin wave, for example, being shallower in the future. So here, going back to the feedbacks, how we may explain changes in the mean with respect to ENSO growth. The top row you already seen. This is 21st century minus 20th century, the three dominant feedbacks: thermocline, zonal advective, and Ekman. On the bottom here, I decompose the feedbacks into each term. So you see for the thermocline, the left column, thermocline depends on the mean upwelling and the anomalous stratification. You see that the anomalous stratification seems to be explaining very well what type of changes we might expect with the thermocline feedback. The reason these signs are opposite is because there's a negative sign in the thermocline equation, in the thermocline feedback term, and pretty much in all advective terms. But you see here also the mean upwelling, W bar, is also negative. So this corresponds very well with what we see with potential expected changes, relaxation of the mean state. Now, if we look at the zonal advective feedback, again, U prime, which is the anomalous zonal current, seems to explain very well what we see with the expected changes in the zonal advective feedback, whereas the mean changes in the zonal temperature gradient, this is the middle bottom plot here, is very small. With the ebb feedback, this is the most interesting because it has lots of structure, the triple top structure, and also supporting, like I mentioned, early growth of the event and persistence of the event well into the spring. It can be explained by both changes in the anomalous upwelling. You see reduction in the anomalous upwelling and, well, negative anomalous upwelling, I should say, as expected because of an increase probably it could be explained here by the increase in the anomalous zonal current. And also you see an enhanced vertical stratification in the mean. So we'll see that later here in this picture. Sorry, this is very busy, but sometimes it's easier to explain with equations. So again, the top row is the same as before, 21st century minus 20th century each feedback. And the middle row is what happens if we just look at changes in the anomalies and just hold changes in the mean state constant. So basically I recomputed each term, but now here for the middle row, I use 20th century climatology. And for the bottom row, I use, again, here just hold the anomalies constant. As you can see, El Nino in the 20th century, the anomalies. But now what happens if we just look at changes in the mean state? So again, for the thermocline, it seems like changes in the anomalies are actually dominating the projected changes in the thermocline feedback. And changes in the mean, basically the mean of upwelling, are just acting as a damping term. For the zonal advective, again, changes in the anomaly seems to be more important. Basically, changes in the anomalous westerly currents seems to explain very well the changes in the backgrounds in the zonal advective term, whereas here changes in the zonal mean temperature are not as important. For the Ekman feedback, I think both are very important. Changes in the mean upwelling is important, and in the mean stratification is important, especially during the growth phase and the demise phase, whereas changes in the anomalous upwelling seems to support extending the event beyond the boreal winter and pushing the event towards the eastern Pacific. Here we kind of change gears. We're trying to understand how these changes in the in each feedbacks, what drives these changes. And one common aspect of El Nino and something that's very important is the stochastic noise forcing of El Nino. It leads to El Nino growth. There has been many studies, especially in the 1990s, looking at optimal patterns of weather noise that could lead to an El Nino. And one of these patterns that is commonly known is a westerly wind burst. These events are shown to be very important for El Nino growth and sustain El Nino growth. And also they are important for sustaining El Nino La Nina asymmetry as well. And there has been studies looking at the role of these westerly wind bursts in each feedback term. So here we look at changes in westerly wind bursts in the future, projected changes in the future. And for this, we use daily data. You need daily data to compute westerly wind bursts. We perform a filtering where we remove a 91-day running mean, and then we use wind anomalies. We average them again along the equator from 2.5 north, 2.5 south, and we only retain wind anomalies or wind stress anomalies in exceedance of 0.03 newtons per meter, which is climatologically a reversal of the trade winds. We only retain anomalies larger than 500 kilometers that persist for a minimum 3 days. Studying changes in westerly wind bursts in the future climate is very difficult. So one way to simplify this is to look at westerly wind burst impact. And one simple way is to compute what is known as Kelvin wave forcing, where we basically integrate the westerly wind burst in a zonal sense and in a temporal sense. westerly wind bursts here are dependent on X, which is zonal, and T, which is temp time. And we can decompose T into the characteristics of downwelling Kelvin wave, where C is a constant, and we use 2.4 meters per second, which is the observed speed of equatorially trapped downwelling Kelvin waves. So we look at changes in the Kelvin wave forcing due to westerly wind bursts. And what we see here, this is again from January to December, this is a climatology. And what we see here is in the 21st century, this model predicts an enhanced westerly wind burst, which will lead to enhanced thermocline feedback and as well as zonal advective feedback. And this is especially true early in the year, like boreal spring and early summer. And by the way, here the contour, the thick line is the ensemble mean, and the color is the ensemble spread. So all ensembles from maximum to minimum. And you see pretty much it's enhanced throughout the year, but mostly in the springtime. So this is consistent with what we see, that this model is predicting an early onset of El Nino and a sustained El Nino well into the boreal spring of next year. And this is also supported of the slower decay of El Nino, especially in the Eastern Pacific. And why is this important? Here on the bottom left, I'm showing you the SST anomaly difference, again, 21st century minus 20th century, and the persistence of the event well into the spring, especially in the Eastern Pacific. And this region has been found to be key in forcing atmospheric teleconnection, especially towards North America, as was found by Lee et al. 2018. So what I'm showing you here is circulation anomalies, 2-meter air temperature anomalies, and precipitation anomalies, the composite for El Nino events. The top row is 20th century, the middle row 21st century, and their difference. And you can see here El Nino is associated with colder anomalies in the winter over the southern US and warm anomalies over the northern portion of the continent, and enhanced precipitation over the southern US. What we expect here in the 21st century is an enhancement of this pattern. As you can see here in the bottom row, you have a stronger upper level divergence as measured by the velocity potential here in the bottom left. This blue color represents a stronger convection and a shift towards the Eastern Pacific, and then a stronger circulation pattern as shown by the string function here. So you have more storminess over the southern US, which tends to decrease air temperature and also enhance the precipitation of the southern US. So you can see here is basically an enhancement of the El Nino signal, what we may expect in the future. So to conclude, the main objective of this work was to better understand the dominant drivers that modulate the projected changes in the spatiotemporal evolution and diversity of El Nino. Our major findings were that El Nino will initiate sooner in the boreal spring, it will grow at a faster rate, and it will persist longer in the Eastern Pacific. So these significant changes are well explained by common feedbacks processes, for example, thermocline, zonal advective, and Ekman feedback. And also they are well explained by a projected increase in the noise forcing, a stochastic noise forcing of the form of westerly wind bursts into the 21st century. And important implications are that the climate impact will most likely be enhanced. It will not, doesn't seem like there is a spatial change in the climate impact, more like an enhanced signal of the impact. And also, this is probably for future work, this last bullet is that the lead time for a skillful forecast for El Nino may be eroded because this seems to, the El Nino event in the future seems to grow at a faster rate. And also the fact that we may have more westerly wind bursts, especially during the spring, this may complicate future predictions of 21st century El Nino. And some future work, we plan to look into El Nino diversity into the 21st century. And this is motivated by, again, work from Sankey Lee. And we're looking at how these different El Nino flavors will change into the future. And these are the 4 common El Nino flavors: the early transitioning, the resurgent, the persistent, and the early terminating. And as you can see here in the scatter plot down here, this is a 2-dimensional distribution. The persistent El Nino seems to increase by 47, up to 47% under anthropogenic forcing, more than any other type of El Nino. And this event is the one that actually has the largest potential for climate impacts. And I'll thank you, everyone.